So we're determining if it has any local maxes or mins or inflection points. So if we're interested in local maxes or mins, what mathematical thing do we have that helps us find local maxes or mins? So what is true about the accumulation at a local max or min? What's true about the accumulation at a local max or min? What did we say last time? What happens to the accumulation? Pauses, right? This is the key. That our amount function or our accumulation pauses when you have a max, and it pauses when you have a min. It's going up, it pauses, it comes down. It's going down, it pauses, it starts coming up again. So what mathematically can we find these places of pause? When the rate of change is 0, right? So we want to find the pauses of J, and we find that by doing the rate of change and setting it equal to 0. So I'm going to go fast. If we're interested in critical points are possibilities for local maxes and mins. We're going to say, where does the function J pause? Or where does the rate of change equal to 0? So I'm going to divide by -3. If I divide by -3, I get x squared minus 6x plus 5. Is that right? And I can just make it can go away because it's equal to 0, right? Since it's equal to 0, I can just divide both sides by -3. Is it? Check my math. So, potential we get that the derivative equals 0 when x equals 1 and x equals 5. But that doesn't tell us what kind of critical value we have or what it gives us in J. So again, the possibilities are local max, local min, or rest stop, right? Or rest stop. So what can we do? Figure out. How am I doing? Into what? Okay. He said I could plug in values near those into the original function. That would work. That could work. I want to use the derivative though to do it. So let's figure out what's happening at x equals 1. If I do an x value to the right and find the derivative, what is the derivative to the right? -15, right? What does that tell me about J to the left? What does that tell me about J to the left of 1? What's happening with J? Decreasing, right? And if I go a little bit to the right of 1, say 2, what do I get there? 36 minus 15 minus 12. Is that 11 or 9 or what? $17. 19? I don't know. I'm guessing. It's positive. It's positive. $36 minus 12 minus 15. 9. Thank you. Okay. What does that tell me about J to the right of 1? So what do I have? I have J is decreasing. So J decreasing, and then at 1 it's 0, and then at 2 increasing. Therefore, local min. Okay, at x equals 2. So what's another way to look at, let's do it, let's just do x equals 2. So then at x equals 2, or I'm sorry, x equals 5. We're going to take j prime of something a little bit less than 5 and j prime of something a little bit greater than 5. So do 4 and 6. Need your calculators here to help me out. So again, this is it right here. We're doing j prime of 4 and 6. Don't everybody do 4. Some people do 6 too. As soon as you get one of those, tell me what it is. 9? Awesome. Do we have confirmation on those? We good? What does it mean? It means to the left of 5. What does this tell me about j? It's the derivative is positive, then j must be increasing. Okay? And then we know j has a pause at 5, right? We know it has a pause at 5, and then j is, with a negative rate, decreasing. So, local max. Okay, so we got a local min at 1, we got a local max at 5. And we're just practicing that reasoning, right? Now we're getting values out of the function, practicing the same reasoning we worked on last week. That if a function is increasing, its derivative is positive. If a function is decreasing, its derivative is negative. Okay, what's another way? Now we just talked about in the Top Hat quiz, another way to confirm a local min. We could look at what? Also, second derivative. What would the second derivative have to be for a local min? What's the rate of change at a local min doing? The rate of change is? But the rate of change is what? No, not positive. Increasing. The rate of change is getting less negative or more positive. And if the rate of change is increasing, then the second derivative is positive, right? So if a function is increasing, what function is increasing? The rate of change is increasing all through there. So including at the bottom, right? So right there at the lowest point, what is the rate of change doing? No, the rate of change. Increasing. It's increasing from negative to positive values. So therefore that second derivative would have to be? If a function is increasing, its derivative is positive. So if the rate of change is increasing, the rate of change is positive. Second derivative is 18 minus 6x. So we could come down here, so using the second derivative would be an alternate way here. Do it in red. We could say j prime, we just need it at 1, right at the critical value. J prime of 1 is 12. Double prime. Means that j of 1, or j prime, is increasing. And if that first derivative is increasing and we have a critical value, it has to be a local minimum. So that's just an alternate way. That's called the second derivative test. Second derivative test is looking at how the second derivative is telling us if we have a local max or min. Same thing over here. J double prime of 5 is what? Negative 12 means that the first derivative is decreasing. And that would confirm local max. First derivative decreasing, getting less negative and more positive. Less positive and more negative. Okay, then we have a place where the second derivative is 0. Where's the second derivative equal to 0? X equals 3. What does it mean? So let's look at second derivative at 2 and second derivative at 4 and see what's happening. Second derivative at 2 is 6. Second derivative at 4 is negative 6. So what happens at x equals 3? So what? We have a positive second derivative, which means increasing rate. Okay? Then we have the second derivative is 0. So what? The rate pauses. So now the rate pauses, and then the rate is decreasing. It's the same set of relationships, right? It's the same set of relationships. If a derivative is positive, the function's increasing. Therefore, the rate of j is increasing. If a derivative is 0, then its function pauses. So the rate pauses. And if a derivative is negative, its function decreases. So the rate decreases. So we got increasing rate, pause of the rate, decreasing rate. And that's an inflection point. So let's see, we had a min, so it's going to look like this. Increasing rate, pause of the rate, decreasing rate. Inflection point at x equals 3. Okay, and then we could take all these values. We could take x equals 1, 3, and 5. So we've got our local min at 1, our inflection point at 3, and our local max at 5, and we could find those values. We're not going to do this, but this is something you should be able to do, no problem for your pre-calc. Get those y values, right? Get those values of that dependent variable, and those would be points on your graph of j. 1 comma j of 1, 3 comma j of 3, 5 comma j of 5. And then with all this that we've got, local min, inflection point, local max, all the concavity, you just make the sketch, right? You can make the sketch through those points. Getting all the concavity correct. And getting your local max, your local min, your inflection point. That's the easy part, right? We laid all the groundwork to just kind of get the dots, connect the dots with the right shape, okay? Questions on this example? Yes, please.
The inflection point is found using the graph of j prime,
No, we found it algebraically by finding where the second derivative is 0, where the rate pauses. So where the rate pauses is where the second derivative equals 0. That's how we found it. Right there. So we found that it was x equals 3 from the second derivative. Other questions? So this stuff over here was second derivative stuff. Okay. If there's no questions, we'll move on to optimization. Erica or Morgan, could you fill up my water bottle, please? Okay, so optimization. Okay, this is a real important topic here. With a function, various values of the independent quantity can be chosen, resulting in corresponding values of the dependent quantity. Very simple, right? So you pick a value, it gives you a corresponding value of the dependent quantity. That's just the idea of function, right? And so this purple function is just, what, a zillion points of a value of the independent quantity and a corresponding value of the dependent quantity in some real-world relationship of quantities, right? So with optimization, what we're asking is we want to find the best value of the dependent variable. What's the best? What's the best value of the dependent variable? Okay? In order to find that, we need to find which value of the independent variable should be chosen to give us the best value of the dependent variable. Okay? This is the idea. So we're after the best value of the dependent variable, and we're asking what value of the independent variable is going to give us that. So we're going to need to know two things for that. First of all, what do we mean by best? So there's two possibilities for best. The maximum or the minimum. All right, so the maximum value or the minimum. In some cases, we want the minimum. That's the best, right? Minimum cost. Thank you. Okay. Of course, we know lots of situations where, we want the maximum profit, maximum area, maximum volume, whatever it is we want. The second question is, what, in this given situation, what interval of the independent variable is relevant? So what values of our independent variable make sense in this situation? And we call that the applicable domain. What is the applicable domain? That's going to be really important. Okay, so let's do some investigation around this stuff to kind of make sense of it. So here we go. So we got this function f. So I want to know what independent variable value would result in. We'll start with max. So here the best is the max. When x goes from, when the applicable domain is 0 to 30. Okay, so if the applicable domain is 0 to 30, then we don't care about this part of the graph. Okay? So answer that with the person next to you. 0 to 30. That's what I'm showing now. What independent variable's value would result in the max value of the dependent variable for this part of the applicable, if the applicable domain is 0 to 30? Okay, what do you think? X equals? They're saying 6.5. What do you think? Over here. If you said 5.5, you were right. Something around 5 or 6. If you said like around 5, 6, something like that, you're right. It's right around 5.5. Does that make sense? That's the value of the independent variable that's going to give us what we're calling the best, the max value. Okay, let's try another one. So now I want to do max again, but now I want the applicable domain to be from 10 to 35. So I'll show you that. Again, we want the max. If the applicable domain is from 10 to 35. Okay, there you go. So what x value from 10 to 35 is going to give us the best, in this case, the maximum value of the dependent variable? 24. 24. We want f to be the biggest it can be. That's all it is. Where is f the biggest it can be? 10. right? Oh, that's all we're saying. We want, here are all the possible output or possible values of the dependent quantity for this applicable domain. We want to make x 10, so we get the largest value of f. You see it? Okay, let's do it again. So now, let's do max again. From 14 to 24. Okay, what do you think? Okay, so from 14 to 24, which x value is going to give us the best? In this case, the maximum. 24. So we kind of have to look for a pattern here. What is happening? Let's go back to the first one. What happened in the first one? 0 to 30. We said 5.5, right? And what is it about 5.5 that makes it the largest value on the applicable domain? What is it about x equals 5.5? What do we have? Okay, yeah, but specifically, what's going on there? What do we call that? Local max, right? Local max. So if we had the function f and we wanted to pinpoint this highest value, what would we do with the function f to pinpoint this highest value? What would we do? Yeah, take the derivative and set it equal to 0 because we want the f to do what? What's f doing there? Pausing. It's pausing in its value. And places where we get a pause of f is where the first derivative is 0. The reason that we do the first derivative equal to 0 is because f pauses. It's not something we memorize. It's something we understand, right? The rate is 0. That means a pause. That if the rate of change is 0, that means f isn't changing for at least a moment, right? F isn't changing for at least a moment. That's a pause. It's a pause in accumulating amount. So if we were to do that, what would happen? We would get x equals 5.5. Is that all? Something like 26.5. And? Yes, thank you. And? 24.5. Okay, well now, that's 3 possibilities. We want to know what's the best. We want to know, so we're imagining that we don't have the graph, we have f, and we're starting to do some mathematics to figure out that the fact that when x is 5.5, we get the maximum value of f. So what can we do then? So I just got 5.5, 16.5, and 24.5. They can't all be the max. How would I figure out which one's the max? Plug it into what? Plug it into the original function and then do what? Look for the largest one, right? Just find these values. F of 5.5, F of 16.5, F of 24.5, and pick the biggest one, right? Pick the one that gives you the maximum value of f. In this case, it would be 5.5. Okay, but then we saw some other examples where maybe this is not going to work. Why not? So what are we doing? We're considering all local maxes and local mins, right? We're considering all local maxes and local mins as possibilities to give us the max on the applicable domain. But I showed you another example where this wasn't the case. What was the next one? 10 to 35. From 10 to 35, where did you say? On that domain, applicable domain right there. From 10 to 35. Where was the maximum there? At 10. Is that, would we find that if we did f prime equals 0? No. So do we have to check every single x value in the applicable domain? So we know we want to check the local maxes and local mins. Do I have to check every x value then? If it's not, here it's not. Here it's not a local max, right? Let's do a min this time. From 0 to 30. Okay, from 0 to 30. What are you going to pick? Is it going to be at a local min? There we go. Where's the, I want the min on this applicable domain 0 to 30. 30. Is it a local min or local max? No. All right, what if I did from 0 to 25? And I want the min from 0 to 25. What's going to find it now? 16.5, right? The local min is going to find it. So when it's not a local min or a local max, are you noticing where that maximum or that minimum is? What's that? Do you see that it's at the end? It's at the end. So it either has to be at a local max or local min, or the other possibility would be it's just at the end, at the start or the end of the domain. Okay? So that's all the examples showed that. Okay? So let's just review it again. We want the best value of the dependent variable. And we want to know which value of the independent variable should be chosen to get the best. But now, we actually want to ask then, what is the list of all possible independent values that might give the best dependent value? What is the list of all possible independent values? We don't want to check every one. It'll take forever, right? We want to narrow down our list. So what's one possibility for an independent value that might give a best dependent value? We just saw it. So what's one possibility? What's that? Critical values, right. Local max or minimum. So we want to check all critical values in the applicable domain. All critical values within the applicable domain might give us the biggest or the lowest value. But then there's another possibility, which is? Right, the starting and ending values of the applicable domain. So what we're going to do is we're going to make this list. And this list will for sure tell us, so after we make this list, then to figure out what the max value or the min value is, we're going to just take this list of x values and just put them all into the function. And if we're after the max, then we're going to choose the one that gives us the highest value. If we're after the min, we're going to choose the one that gives us the lowest value. Okay, so these problems are really all about this function f, okay? We're going to do these optimization application problems, and they cover a wide range of topics, okay? But what's the same about all of them? What's the same about all of them? Every optimization problem is about defining and using this function, whose dependent variable is the quantity to be maximized or minimized. It's all about this function f, right? And what is it about f? The dependent variable of f is the quantity we're trying to make the biggest or the smallest. And so half the problem, you'll be taking the information and you'll be building the function f. And then the second half of the problem, you'll be using f like this. You'll be getting your list of candidates for the independent variable that are going to give you the possibilities for the largest or smallest value of f. So the first half of the problem is creating f. Second half of the problem is writing f to find its greatest or least value in the applicable domain. Okay? So when you come to an optimization problem, this is like, okay, I got to get that function f. And what is it about f? The dependent variable of f is the quantity I'm trying to maximize or minimize. The y value on the graph. Okay? Here we go. What two non-negative numbers, a and b, whose sum is 25, maximize the value of 2a squared plus b squared? Minimize. Okay, so what is this problem all about? What is this problem all about? Anyone want to give it a shot? Every optimization problem is about what? Yeah. Nope, that's a more specific detail. What is this problem all about? No. It's about defining and using a function whose dependent variable is the quantity to be maximized or minimized. It's about a function. It's about a function. It's all about a function. First we're going to define it, then we're going to use it and do these things that they were saying. So, all right, so we need a function, and what do we know about this function? The dependent variable of the function is the thing we're trying to maximize or minimize. Trust me, I am helping you if you listen and tune in. You're trying to create a function whose dependent variable, or if you want to, the output is the quantity that we're trying to maximize or minimize. What is the quantity we're trying to maximize or minimize? 2a squared plus b squared. It says we want the maximum value of 2a squared plus b squared, or the minimum value of it. So we need our function to, its dependent variable, or its output, to be 2a squared plus b squared. So if we call it f, so what in general defines f? What in general defines f? What's the rule for f? You're looking at it, 2a squared plus b squared. Why? Because that's the thing we're trying to maximize or minimize. Okay, but there's a problem with this. What's the problem with this? Yeah, so part of getting this function is to get it in just in terms of one variable instead of two. Right now it's in terms of two. So it'd be really nice if we could have it say just in a, right? If we could just get f of a. And what does that mean? Well, 2a squared is fine. Well, then we just need b in terms of a. If we could get b in terms of a, then we'd have our function, right? If we could get b in terms of a, then we'd have this function that's going to be the centerpiece of the whole problem. So we need a relationship of b and a. What's the relationship of b and a? A plus b is 25. So b is This is setup work. This is not primary, okay? It's not, we got two equations here, and they're both equally important. No, the function is central, primary. This is just another relationship of a and b to help us with that function, right? So it's 2a squared plus 25 minus a squared. Now we've got it. We got half the problem done because we found the function. Half the problem is finding the function. Second half, using it to answer the question. So if we want to maximize, we want to maximize f, what are we going to do? But actually, I forgot. Along with the function, we need that applicable domain. So when we find that function, we also need the applicable domain. So what that means is all possible values of the input variable. So a is going to go from what to what? What are the possible values of a? Non-negative, so 0. That's the smallest it could be. And how big could possibly a be? Yeah, if b were 0, then a could be 25. So now, what are our possibilities for possible candidates for a for maximum and minimum? Possible candidates for a for maximum and minimum will come from two places: critical values, endpoints, right? Or starting at any value. So we want critical values. Critical values are, this is the easy part, right? Chain rule. You know what to multiply that out. Use the chain rule. But then if we want to set equal to 0, it's fine. Right? And set equal to 0 to get critical values. So I have 4a plus 50. This times minus. So minus 50 plus 2a. Or 6a minus 50. Critical values, how many do we have? Just one. 50 over 6, or 25 over 3. Is that 8.333? Leave it 25 over 3. Okay, how can we figure out what kind of critical value that is? A couple different ways. If we put that into the derivative, what are we going to get? We get 0. We already know that. So we could use the second derivative, right? But actually we don't need to do this, okay? Why? Because we just need the list of all possible candidates, and then we'll just find the biggest and the smallest. Yeah, so let's do that. That's better. Less work. So what are other possible candidates? So this is critical values. And what other possibilities do we have? The ends. End values are 0 and 25. So we have our list of candidates. 25 thirds, 0, and 25. And so what are we going to do? We're going to do f of each of those. So f of 0, f of 25 thirds, and f of 25. The maximum and minimum of f on that domain has to come from one of those three a values. Okay, so what's f of 0? 625. Anybody have the second one? F of 25 is 1250. Anybody have this middle one in the middle? Nice and loud?
294.14.
Anybody else get that? Someone else do it, please. Make sure. You get 347. Anybody else? Yeah. What is this saying? What is that saying? Is that plugging into the derivative? Yeah. 416. 416. Okay, are we good now? Yes, ma'am. Yeah. We're evaluating the function at 0, right? And then evaluating the function at 25 thirds, and then evaluating the function at 25. How would you what? No, we have it in terms of A only. Yeah, this is our function now. Remember, this is the centerpiece of our solution. A function of one variable whose dependent variable is the thing we're trying to maximize or minimize. So that's the one you want to use, the one in one variable. Okay, so conclusion. The maximum value of 2a squared plus b squared is 1250, and occurs where? And that occurs when a is 25. And the minimum occurs? The minimum is 416, and occurs when? A is 25 thirds. So again, this is the whole ball of wax. Every problem is in a totally different context, but this is always your goal, this function, whose dependent quantity is that quantity that you're trying to optimize, make the best or the worst, or the least or the greatest. You need to get that in one variable. Other relationships are just there to help you get that function in one variable. This is the key relationship here. Then we're going to find the critical values and the endpoints, the end values, and get all possible values of the function, and pick the biggest and the smallest.